I'm Mark Kavanaugh for Tavi Coaches, and today I'm going to coach you up on electric fields. In this video, we're going to talk about electric fields, drawing the field lines in those fields, and calculating the value of electric fields using vector addition. So let's start with a field that we're familiar with. We'll start with the gravitational field. So in a gravitational field, we know that the gravitational force is just a mass of an object times the acceleration due to gravity, or the gravitational field strength constant, and that's near the Earth's surface. And we can rearrange that equation to have Fg divided by the mass of the object. So if we look at a situation where we drop objects in a gravitational field, we know that the gravitational field strength constant is a value that does not change because the gravitational field is constant on or near the Earth's surface. And G, the gravitational field strength, we know is 9.8, and that's the amount of gravitational force per kilogram of mass. So 9.8 newtons of force for every kilogram of mass. Now, if we draw those field lines, we can see that the field lines for the gravitational field always point down close to the Earth's surface. So if we look beyond the surface and into space, what we know is that on the surface, Fg is equal to the mass times the acceleration due to gravity. But when we go out into space and we put a satellite out in space 2 radii from the Earth, so the distance it is from the center of the Earth is 2r, what we know is that the G value is going to change because it's further into the space. So we can use Newton's law of gravitation to calculate that gravitational force, where with the mass of the object and the mass of the Earth are taken into account, we know the mass of the object is used on both sides of the equation. So we know that the mass of the object is very small in comparison to the mass of the Earth. This is important when transitioning to electric fields. Now, the mass of the object is on both sides of the equation, so we can cancel it out. And that leaves us with G is equal to the universal gravitation constant times the mass of the object, in this case the Earth, divided by the radius squared. So the Earth is what supplies the gravitational field, so that is what's used in calculating the gravitational field strength constant. Now, if we draw field lines when we're in space, we know that the gravitational field points towards the center of the Earth. So all of the field lines would be pointing towards the Earth from any point around the Earth. So this is what the gravitational field lines would look like. Now, if we change the distance and move further into space, we can see that the G value is proportional to the inverse square of the radius. So that means if the distance doubles, that means the gravitational field strength constant is going to be 1/4, because we're going to do the inverse of double squared, so that's 1/4 is strong. So it's not going to be as strong the further we get out into space. Let's transition this to electric fields. So the gravitational fields, remember, G is equal to the constant times the mass of the object divided by the distance squared, where the mass of the object is very small in comparison to the mass of the Earth. And we know those field lines point towards the center of the Earth. In a constant gravitational field, we know that G is equal to Fg divided by the mass of the object, and the gravitational field strength is the amount of force per kilogram of mass, and that field is pointed constantly downward. So transitioning that to electric fields, G, the gravitational field strength constant, is equivalent to E, which is the electric field strength. And we have mass of the object, that would be the mass of the source of gravity. This is going to be the charge of the source. And then we have the distance is still related to the inverse square for each of the fields. And then we have the constant G, which is going to equal our constant K, or equivalent to our constant K. And K is Coulomb's law constant. So the gravitational field strength constant at constant gravitational field, E, is going to equal the electric force in the field. So mass is equivalent to charge in electric fields. And the difference between the charges, Q naught is the source charge that is in the field, whereas capital Q is the charge that is producing the field, much like the Earth produces the gravitational field, and any object in that would be considered the mass of the object. Now, electric field strength is the amount of electric force per coulomb of charge, much like gravitational field strength is the amount of gravitational force per kilogram of mass. And we know that Q naught is very small charge in comparison to the source charge for the electric field. And we know that Coulomb's law constant is also equivalent to 1 over 4 pi epsilon naught, so we can also calculate the electric field strength in this manner as well. So if we break down the electric fields compared to gravitational fields, the only difference we have is that mass is the charge equivalent in electric fields, and the gravitational field strength is equivalent to the electric field strength. Now, if we use Coulomb's law to calculate the force of a charge in a field, we know that Q1 can be the source charge. So this is what's producing the field, much like the mass of the Earth produces the gravitational field. And then the electrostatic force Q2 would be the charge that is in the field, much like any object that is in a gravitational field. And then we can substitute in for force Q naught times the electric field from our equation, and Q naughts are going to cancel out, leaving us with the equation for electric field is K times the source charge divided by the square of the distance between the centers of the charge. And this is used to calculate the electric field strength any distance from a source charge. The Fe equals Q naught times E, that's used to calculate the electric force on a test charge that is in an electric field with strength E. So this is the difference between fields and forces, is that the field is calculated using one charge, and we need the charge that is in the field to be calculating the value of the force on that charge. Now, why do we use fields? Well, we kind of just answered this question. Is forces exist only when two or more particles are present. So to calculate a gravitational force, we need two masses. To calculate an electric force between two charged objects, we need two charged objects. And fields exist even if there's no force present. So the field of a single particle can be calculated. So this is why we use fields instead of forces, because we can calculate a value of electric field anywhere near a source charge. We don't need a second charge to be able to calculate the field like we do to calculate gravitational or electric force. So let's look at how we draw electric field lines. We saw that with the gravitational example, where the gravitational field lines point towards the Earth when we are out in space. Now, the electric field lines from a source charge, since gravity is only attractive, we know that we can have attractive and repulsive forces with fields. So if we have a positive charge, a small positive charge, close to a much larger source charge, those field lines are going to point away. That's going to show tangentially the force or field that is applied to a charge in that field. Now, if we look at a negative source charge with that same positive, what we know is that the field lines are going to point towards, because that's the way that the force or field is going to be directed for a positive charge. So the field lines are drawn in the direction in which the positive charge would be impacted. And we know that for positive charges, the field lines are directed away and from the charge, and negative source charges have the direction pointed towards. And the electric field is tangent to the field lines. So the field lines show the direction, and the force is also tangent. So in this case, when we have one source charge, the field only depends if it's positive or negative source charge on direction of those field lines. Electric field lines, some confusion that might arise is that the field vector is tangent to the field lines at each point in space. So the field lines are not vectors. So in the case of one source charge, the field lines are straight lines, but the field at any point, the charge may be moving through the field and not just being impacted directly. Now, the second part, the number of lines through the area, is proportional to the strength of the field and the source charge. So if we look at these two charges, we can see that based on the number of field lines that are directed away, the bottom charge has twice as many field lines pointing away from it as the top charge, which means that its charge is twice as great as the charge above. So all we have to do is count the number of field lines, and that tells us proportionally how those charges are related. So the bottom charge has twice as much charge as the top charge. Now, unlike being near Earth with only one gravitational field, what if there are two or more source charges? So if we have a positive and a negative charge, what would the field lines look like in this scenario? So we know that there's going to be a field line that is going to be directed straight from the positive charge to the negative charge, but those other field lines that would point out like spokes, now they're going to be impacted by both charges. So field lines that would point away from the positive charge are going to then curve and move towards the negative charge. So the electric field is going to look like this. Now the field lines on the backside are also going to curve away from a positive charge and towards the negative charge. So an electric field produced by two charges is going to look like this. So they're not just straight lines. And this is known as an electric dipole because we have two source charges. So if there's two source charges, this is what our field lines are going to look like. Now, what if we have two positive charges? What do the field lines look like in this scenario? Well, we know that the field lines are going to point away. So what happens is as they point away, they're going to curve away from the other source charge. So our field lines look like this, where we only have that horizontal line pointing on the back sides of each of the charges pointing away, which means in the middle, we'd have a spot where the electric field would be canceled out because we'd have the same value of charge of producing a field in opposite directions. Now, the electric field vectors, the field lines, again, are not the vectors. A vector can be drawn tangent to the field lines to show the direction of the field and electric force. So if we look at the dipole with opposite charges, we can draw a vector that's tangent to those field lines, and this would show the direction of the field and the force. Now, the reason this isn't the direction that it moves is because what if we have a charge moving through the field from the bottom of the page to the top of the page? Well, at that point in time, that would be the direction of the force when it reaches those specific spots. So we know that the charge isn't going to move along those field lines when it's already moving through the field. That's just the direction of the field and force at those points. The electric field lines do not show the path that the charge moves. It just shows that the field lines represent the electric field direction as well as the force direction. And the vectors drawn in the field represent the direction of the net electric force on the charge at that point as well. Now, to calculate the net electric field, we're going to look at an example, and we're going to find the net electric field between the two 1.2 microcoulomb charges. So one of those being positive and one of those being negative. So if those are both 2 meters apart from each other, the centers are 2 meters apart, that means that the midpoint between them is going to be 1 meter from each of their centers. So the positive charge is going to have a field that points towards the negative charge, and then we know that the negative charge is going to have a field that induces towards the negative charge as well. So those two vectors represent the total electric field in space for that point. And what we can do is just do the vector sum of those values by calculating the electric field for both the positive and the negative charge at that point in space. So we can use our equations kq divided by r squared, and we know that each of them are going to have the same magnitude because they have the same value of charge. So we're going to take the absolute value of the charge, and we'll calculate using kq divided by r squared, and we'll find the value for each of them is 10,800 newtons per coulomb. So each vector pointing the same direction, now we can just do the vector sum of those and add them together to get our 21,600 newtons per coulomb, 1 meter between two source charges in a dipole. So let's look at a different example. We want to find the magnitude and direction of the horizontal field on a point P from the horizontal. So we have two charges, negative 4 microcoulomb at 0.2 meters and a positive 7 microcoulomb at 0.4 meters away from some point in space. We'll call it P. So what we're going to do is we're going to draw vectors that represent the field at that point in space. So we know the positive charge is going to have one pointing directly up, and the negative charge will have one pointing to the right towards it. So what we need to do is, with the positive charge up and the negative charge to the right, since they're not pointing in the same plane, what we have to do is do vector addition. So So we're going to draw the positive and the negative, and what we've created is a right triangle because the field is going to be this total that's going to be the hypotenuse of our triangle. So what we're trying to do is find the magnitude of the net electric field at that point. So we're going to use our same equation, E equals kq divided by r squared, to calculate each of the individual vectors. So we'll start with the 7 microcoulomb and substitute in the distances and the charges and Coulomb's law constant to get our value. Then we'll do the same thing for the -4 microcoulomb. Remember, we're just doing absolute values of the charges, and we'll get that value of 9 times 10 to the 5th newtons per coulomb. So now all we need to do is Pythagorean theorem to find the net electric field for point P. So a squared plus b squared is going to equal c squared, and to find the electric field total, we're just going to take the square root of both sides. And then we can evaluate to find the value of the electric field at point P, which is 9.82 times 10 to the 5th newtons per coulomb. Now, that's the magnitude, but we also want to find the direction. And it says the direction from point P along the horizontal. So what we're trying to find is the angle from the horizontal axis. So this angle from the E total and the negative field line is going to be the angle that we're going to find on our triangle. Now to find it, we have all three sides of a right triangle, so we can use any one of our trig functions to do inverse trig. I've chose to do the inverse tangent in this video, which you could have done inverse sine or cosine, but inverse tangent is opposite over adjacent, and when we do that, we find that the angle is 23.6 degrees from the horizontal. So the total is 9.82 times 10 to the 5th newtons per coulomb at a 23.6 degree angle from the horizontal, and that's the magnitude and direction for the electric field at point P. So recapping electric fields. First, the electric field only needs one source charge to be calculated, unlike electrostatic force where we need two source charges to calculate force. The field lines point away from positive charges and towards negative charges. The field lines of a dipole are curved. The lines only show the field. The direction of the force is tangent to those field lines, and a field vector would also be tangent. Calculating the electric fields, we first draw a diagram for each charge at the given point, then calculate each individual electric field at that point using our equation, E equals kq divided by r squared, and then we use vector addition to find the total electric field. So this is calculating electric fields and an introduction to electric fields and field lines. I hope this is helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X at Cavi Coaches.